Okay. Okay, so welcome to the afternoon. Sorry for a small delay. And yeah, we will have two lectures in the afternoon. And the first one will be by Shruti, who will lead another discussion of the introduction to scattering amplitude, starting with the recursion relations.
Okay. Can everyone hear me okay? Yeah? And see everything? Okay. Good. So today I wanted to talk about recursion relations. And unlike the stuff that Yaroslav introduced to us in the morning, this is not going to be as general for the simple reason that recursion relations are only possible when you have some special property of the theory that you're dealing with, usually some kind of symmetry. So I'll be more precise in a minute. So the primary example that we'll be studying is going to be Yang-Mills. Okay, and as all of you are familiar with, Yang-Mills has two kinds of interaction terms, right? You have a cubic interaction that looks like this. And you have a quartic interaction. Right? So one thing that you should notice right away over here is that this coupling over here, your quartic coupling, is not a generic coupling, right? It is related to, yeah. Okay. Okay. I won't correct this because this is Yang-Mills, but going forward, I'll write a little bigger. Okay, yeah. So as I was saying, so this is not a generic quartic coupling, right? This is related to the cubic coupling, and it's related because this is a gauge invariant action. Another thing to notice is that there is nothing at order field to the fifth or field to the sixth or anything else, right? This is missing. So this is largely something that we can already see when we look at the Parke-Taylor amplitude, for example. It's actually something that you can see completely on shell, okay? And that's kind of the idea behind recursion relations, where when you have interactions that are related to one another, especially interactions where the n-point interaction is related to the n-1 point interaction, then you can set up a recursion relation and you can figure out all the amplitudes based on lower point amplitudes. Okay, and there was already a question about this when Yaroslav was talking about this as to, sure, you can have a 4-point amplitude, and you know how that factorizes into 3-point times 3-point over some pole. But it's not really practical to keep doing this up to n point. That's practically not possible, right? So how do you say that a theory exists or doesn't exist? These recursion relations will be very powerful in doing that, because you'll be able to say something about n-point amplitudes just based on some properties of the theory and the 3-point interactions or 4-point interactions. Okay, so what do I mean by factorization? We talked a little bit about this at 4-point, right? I'm going to just go directly to n-point, actually. And the first thing I want to get ahead of is that if you have an amplitude, an, right, this is going to be dressed with all kinds of color factors. And what I want to do is look at a trace decomposition, right? So I'll have some trace of some generators over here times an amplitude that I'm going to call the partial amplitude, and I'm going to denote that with these square brackets instead of round brackets, okay? So something like 1 sigma n. So we already saw this in Hendrik's lectures. Good. So how does factorization work when you have color ordering? It's slightly different. The reason it's different, you can already see at 4 points. So let's look at some 4-point amplitude like this, and look at the ordering 1, 2, 3, 4. Okay? So actually, before I write it in factorized form, let me just write it as a contact contribution like this. Okay. So what kind of factorization channels can I possibly have? I can only have factorization channels where adjacent legs give rise to an intermediate momentum that is going on shell, right? So I can only have a 1,2 pole and a 1,4 pole, right? So I can't have a T pole in a color ordered amplitude, which is A4, 1, 2, 3, 4, right? Because I'm only looking at color ordered objects. Now the whole fully color dressed amplitude is going to have all of the poles as you'd expect angles to have, but the partial amplitudes won't. Okay, so what happens to Parke-Taylor? So I'll just remind you that Parke-Taylor was an endpoint amplitude where you had 1, 2, 3 to n. The first two were minus helicities, and the rest were all positive helicities. Okay? And we only saw this for 6-point, so I'm just going to write down the 6-point formula first. Okay, so this is familiar from the morning. Now this is when you look at this, it's clear how this might generalize to endpoint, right? All you need to do is continue to have your angle 1, 2 to the power 4 on top, and then at the bottom, you have all of these brackets all the way until n minus 1, n, 1. Okay, so how do I check that such a amplitude is actually the correct amplitude for an endpoint? So this is called maximal helicity violation. We'll talk about why. But for now, this is what I'm going to call an MHV amplitude. I'll try not to, but if I use the terminology, this is what I mean, this helicity assignment. So, okay, so how do I check that this is correct? Okay, and there are two ingredients to checking whether this is correct. One is factorization, and the other is contact terms. So I should specify that I am specifically talking about tree-level amplitudes throughout this lecture. Okay. Yeah. Yeah, good. So I probably should not have said equal to. I should have said contributes to. Yeah. So these are the only pole terms that will contribute to the 4-point amplitude once you have a color-ordered amplitude. Okay. So let me start with factorization. So what kind of factorizations or what kind of factorization channels does this have? So one kind that it has is you have a 1 minus, n plus, 2 minus, and the rest of them on this side are all pluses. Right? Now, because this is Yang-Mills, this can either be plus or minus, but this can actually only be minus. Okay? Again, recursion will tell you why this is the case, but for now, bear with me. So this is one of the factorization channels. And we saw that because this is a 3-point amplitude, right? This amplitude is fully fixed by little group scaling. So this amplitude is going to be np cubed over n1 p1. Good. So that's the 3-point amplitude. This one over here, assuming that Parke-Taylor actually works, is just going to be the Parke-Taylor amplitude, but at n minus 1 point, right? Good. So that gives you 2p to the 4th, and then all of the cyclic stuff at the bottom. So let me go in the opposite direction. So p2, 2, 3, all the way up to n minus 1p. Good? Yeah. So now the last ingredient of this factorization channel is, of course, the propagator. So that is 1n, 1n. Okay? So it's pretty simple to see that various things cancel over here. And of course, you have to use the fact that P is actually P1 plus Pn, right? Because that's the factorization channel that you're on. And when you do that, you'll see that this actually gives rise to the endpoint Parke-Taylor factor. Okay? So this is not a proof of the Parke-Taylor factor. All this is saying is that if you have a Parke-Taylor amplitude, it's one n pole. When you sit on that one n pole, you are going to factorize correctly into a 3-point amplitude and an n minus 1-point amplitude. Okay? So that's the first step. The first step is checking that whatever amplitude you have actually factorizes correctly. Okay? So all of the other poles in the Parke-Taylor amplitude, sensibly, because we are in color ordering, they're only adjacent poles, right? So only 1, 2, 2, 3, 3, 4. So there's no 1, 3 pole because that's not possible in a color ordered amplitude. Okay. Good. So the second step is contact terms. So we haven't actually talked about contact contributions, though there was a question about it. The basic thing is that an amplitude in general can be written as some pole terms and some contact terms. Okay? So we already checked that whatever contribution to Parke-Taylor, so this kinematic structure over here takes care of all of the poles, right? But we haven't checked whether there's any contact contribution I can add to Yang-Mills. Now, if you look at the Lagrangian, it becomes very obvious there's actually nothing else you can add without adding a new coupling constant, right? Because if I add another coupling constant, it's not going to be G. It'll have to be some other coupling. It'll have mass dimension, unlike this one over here. It's going to have to be some high derivative operator. From the point of view of amplitudes, all you have to check is there any kinematic structure that I can add over here that has the right mass dimension? Okay, so what is the expected mass dimension? So at n point, the mass dimension of an amplitude is 4 minus n, and that will generically be equal to the mass dimension of the coupling plus the mass dimension of whatever kinematic part of the amplitude is there. So over here, because we're in Yang-Mills, this is 0. Okay, so you need to have a kinematic structure with mass dimension 4 minus n. And it's easy to check. I mean, like this is, I'm pretty sure all of you can see that 4 minus n is less than 0 when n is greater than 4. So once I go beyond 4 point, there is no possible contact contribution that is local that I can write down. Okay, and that is exactly what we see from the point of view of the Lagrangian as well. Okay, so far this is all making sense. You can actually see the fact that Yang-Mills has to be gauge invariant in this helicity sector just based on this pretty simple argument, right? So just based on the fact that you factorize correctly and there's no contact term you can add. Okay, so already over here, you kind of saw that there was a recursive step, right? I needed to use the fact that this amplitude works at n minus 1 point to show that it works at n point. Good. So how do I implement this in a sort of automatic fashion, and how do I go beyond this very simple helicity sector? Okay, and for that, we're going to look at BCFW shifts. So this is named after Brito, Cauchy, Feng, and Witten. And it's basically, the idea is that we're going to introduce some complex parameter, Z, and we're going to shift our spinors of two particular external legs of our amplitude. So in this case, I'm going to choose I. Okay, maybe I should say I and J. and I'm going to shift them in this way. Okay, so this is Z. This is some complex parameter that I have introduced, and I'm going to use the fact that now my amplitude is going to be a function of this parameter, and it's going to be analytic in this parameter to set up a recursion relation. Okay, that's where we're going with this. But before that, you should recognize that this shift is actually very special. Okay, the reason that it's special is because all the nice properties that we learned spinor helicity variables have continue to be true when you introduce this parameter z, right? So if you have, like, for example, I with I, you know that needs to be 0. That is clearly satisfied, okay? You can check that this is true of j with j as well, and this is more non-trivial, but you can check that it's true, okay? So this means that the momenta that these correspond to, the shifted momenta, so pi tilde and pj tilde, are going to be null. The next thing that is nice about this shift is that it's actually going to preserve, I shouldn't use I, A. It's going to preserve momentum conservation, or rather it's going to continue to conserve momentum. So this is the statement of the sum of all of the external momenta, right? And you would want this to be equal to 0 for momentum conservation to hold, and you want this to continue to be true when I shift my brackets, right? And you'll see that this is actually true because the contribution you get will be the usual momentum plus I j z minus z I j. Okay, so these will cancel. This is already 0, so this is 0. Okay, so all this basically to say that yes, I have analytically continued my amplitude when I introduce the z variable in my external spinors, but for every value of z, I'm still on shell. Okay, so I've not changed the fact that the amplitude is a well-defined object only on shell. It's still on the support of the delta function that conserves momentum, and it's still null. Okay, good. So obviously, the actual amplitude we're interested in is not an of z. This is some shifted, non-physical, weird object. What we really want is z equals 0, right? That's the physical. That's where the physical amplitude lies. And because z is complex and the amplitude is an analytic function of z, I can just say that an of 0 is this integral, this contour integral, where the contour goes around z equals 0, right? And then an of z will just pick up, the only residue that this contour will pick up, as long as it's close enough to 0, is z equals 0. And so that'll give you your unshifted physical amplitude, right? Okay, so good. So I have a situation now where on the z plane, I have this contour here around 0. Presumably, an of z has other poles elsewhere, right? Yeah. Sure. Yeah. Yes. 1 over 2 pi I. Is that okay? Good. So good. So you have poles elsewhere. You have a pole here, and this is the contour that you're looking at. Now, what I want to do is use Cauchy's theorem to take this contour, to reverse this contour, and basically pick up only the poles outside z equals 0. Okay. Now, what are these poles? We already know what these poles are because we know that the amplitude looks like poles at the points of intermediate momenta going on shell and contact terms. Contact terms are local, so they don't have any poles in them. So the only poles that exist are when intermediate momenta go on shell. Okay, so let's explicitly see, or actually I should have said, it's when the only possible poles are when intermediate momenta go on shell. Okay, so the intermediate momenta is something like pi square, right? This is some intermediate line like this one over here. Yeah. And immediately you'll notice that, so this is the type of pole that we're interested in investigating. But you'll notice that if pi contains p little I and pj, then this actually adds up to something that doesn't depend on z. Okay? So actually, when both I and j are on the same side of the factorization channel, I'm not going to get a pole of any kind in this an of z, right? So the only time I will is when I'm looking at factorization channels, this is schematic, like this, where I is on one side and j is on the other side, okay? And in that case, I'll get a pole that looks like 1 over pi square of z, and you can check that this is actually going to be a simple pole. Okay. So the form of the simple pole, so okay, let me write here. So pi square of z will take the form some simple pole in z over pi square zi. Okay, where zi is the location of the pole. Okay, it's going to be, when we do an example, very clear how to find out what zi is. For the time being, it's the location of all of these poles, right? Okay, yeah. Good. So it's completely unobvious that that is true. Okay. So yes, these are the physical poles, but you can, as he said, have a pole when z goes to infinity. Okay. So good. So for the time being, let's just say that this goes to 0 when z goes to infinity. We'll justify this statement, and we'll see that it's a very non-generic statement. It's something very special about Yang-Mills that has to be true, or whatever theory you're recursing for that matter, actually. Good. So, yeah. Yes, so we'll see, like in gravity, for example, you have an infinite set of contact terms, and this type of argument will still work. So, yeah. But of course, Yang-Mills is slightly simpler because actually it doesn't have contact terms. But gravity will, and there are other examples which have an infinite set of contact terms that you can still recurse. Yeah, I mean, depends on what you mean. So the BCFW recursion will only have pole terms. You're never going to include a contact term because any kind of contact term will have to come from a z equals infinity pole, and we're saying that this kind of argument only works when there is no such pole, right? So, yeah, so, okay, one second. Let me just say what I was saying a little more clearly. What I'm saying is that the residue of this amplitude at these intermediate momenta points is going to be some pole-looking contribution, right? This is what it's going to look like. Where this is, yeah, so this is actually at zi. Yeah? So in that sense, the only contributions to this integral are going to come from so-called pole terms, right? But that doesn't mean that every term over here is going to look like a pole term. It could look like a contact term, right? You could always have something like Sij times, I don't know. Okay, how about Sij square over Sij, and that gives you Sij. So though it started off looking like a pole term, it could end up looking like some contact contribution. Okay? Right. So so the fact that the amplitudes vanish is going to be, as I said, a special property. So I'll show it in the case of Yang-Mills, but not in the case of gravity. But it has been shown in the case of gravity as well. Yeah. For now, let's assume that this is true. And I'll show in a little while that this is true for Yang-Mills. Yeah. For the momentum. So actually I could. No, it's pretty simple. It's basically you can read it off from here already because this is pi, right? Well, it's pi mu sigma mu. So this already tells you, and because I angle is not shifted, so it's just I plus Zij. That tells you what PIAA dot is. And and this is just PI, right? And this is some other vector. I don't know what vector, it's some vector, right? And you can figure out in that way what that vector is. Yeah, sorry.
You can show that it's perpendicular to the two momenta.
Yeah.
So if you think of the two momenta as coming together in their center of mass frame, it's perpendicular. It's actually like a polarization vector you would use for one or the other.
Yeah. Yeah, so in the case of, which we'll hopefully get to, all line shifts, not just two line shifts, that's going to be an important property that fixes what kinds of shifts I'm even allowed to do. In some sense, I just threw BCFW on the board and said, look, it has nice properties. I didn't construct it for you, right? So we'll see a more constructive version when we do all line shifts. Yeah. Any other? Yeah. Oh, I'm so sorry. I think my handwriting is not good. It's the residue. So the residue at z equals zi of an of z is a left times a right. I will tell you what that is in a minute, at zi over pi square. So this is the picture that I have in mind. You have some left amplitude. You have a right amplitude. And this is the intermediate momenta pi that's flowing in some direction. Right? So I'm looking at the factorization channel where this has gone on shell. Right? And that happens when z equals zi, which is why I'm looking at the residue of this shifted amplitude at z equals zi. And when this happens, I know that the amplitude is going to factorize into the product of two amplitudes. And I'm calling those lower point amplitudes a left and a right. Yeah. Okay. Good. So, yeah. Okay. So we've kind of gotten to the basic, the kind of formula of BCFW, which is the residue formula that I wrote at the end. Okay? And again, this is assuming that the residue at infinity doesn't exist. The residue is 0 at infinity. Good. So let me just write it down here. We've said that an of 0 is a sum over I, where I is various different factorization channels. AL at zi, AR at zi over pi square. Okay? Importantly, pi square is not evaluated as zi, it's just actually pi square unshifted. Okay? And you can do the algebra over there to show that this is actually the unshifted pi square. Okay. Good. So now we are actually in the position to prove the Parke-Taylor formula. Okay? The way that we're going to do that is to first see what kinds of factorization channels would contribute to a BCFW construction of Parke-Taylor. Okay? Now, that depends on what I'm choosing I and j to be, right? Because depending on what I and j are, the fact that your factorization channels have to have I and j on different sides of the diagram is going to decide what terms you have in your BCFW expansion and which ones you don't. So in our case, let's shift 1. So 1 will be 1 plus zn, and let's shift n minus z1. Okay? And I'll remind you that this means that the angle 1 is unshifted and the square n is unshifted. Okay? And the amplitude that I'm trying to construct is 1 minus 2 minus 3 plus all the way to n plus. Yeah? So this has exactly one factorization channel that we have to consider. That is 1 shifted 1, 2 minus all the way to n minus 2 plus, and then the other two are going to be on this side. So this is going to be n hat plus n minus 1 plus. This is what I'm calling I, or pi. Okay? Now, the reason this is the only diagram possible, you'll have to convince yourself that that's true, is because you can't have Yang-Mills amplitudes with all plus or all but 1 plus helicity assignments, unless you're at 3-point. Okay? Which is why the only contribution on this side is a 3-point amplitude. Okay? So, good. So right now, then, we're in a position to just apply our formula, right? What does our formula say? It says that you sum over all possible factorization channels. In this case, we have only one factorization channel. And then you put the amplitudes on either side. So this is going to be our recursive step, right? This is going to be the n minus 1 point MHV amplitude. And it'll basically be a copy of that calculation, except now with shifted momenta instead of regular momenta. Okay, so here you have 1 twiddle 2 to the 4th, 1 twiddle 2, 3, all the way up to n minus 2 p hat, and then p hat 1 hat. Okay, and then on this side you'll have, again, the amplitude that is fixed by little group. So this is n hat n minus 1 cubed over n hat p hat. Okay. Now there are a few, sorry if this is too small, but there are a few simplifications that you can do over here. The first is that the angle 1 is actually not shifted. So this is not a shifted angle bracket, this is not a shifted angle bracket. And this is not a shifted angle bracket. Similarly, on this side for n, the square bracket of n is not shifted. So actually, this is going to be not shifted. Yeah. So all you need to take care of is p hat. And I'll just remind you that p hat equals pn hat plus pn minus 1, right? Because this is just a 2-particle factorization channel. Good. So you can now combine this factor with this one and this with this, and you can see that this actually doesn't lead to any, I mean, you won't get any contribution from any hatted variables, and you'll get just the Parke-Taylor factor over here. Okay. Now, at the face of it, this calculation looks very similar to the one we did over there. Okay, but it's not, because here we actually use the fact that the amplitude, once you shift it, that it doesn't have a pole at infinity. Okay, good. So this is actually the final answer. I've not checked the factorization. I have proved the Parke-Taylor formula. Yeah. because it's color ordered. So yeah, so I can't have any factorization channels that look like n with any of these guys. Yeah, yeah. Yes, yes. You need the propagator, and it needs to be the unshifted propagator. Good catch. Yeah, indeed. So that's actually what's going to give you this angle bracket over here is very necessary to be right here for it to be a full endpoint Parke-Taylor factor. Yeah. Okay. So good. This is nice. We've now seen how you can use these kind of shift arguments to show something that is true for all endpoint. Yeah. Okay. Okay. So Yaroslav was definitely right. I'm going very slowly, but yeah, as long as we all understand what's going on, that's what's important. Okay. So what happens beyond MHV? So I just want to point out that. Okay, actually, let me save that for later. So right now, let's just talk about what happens beyond MHV. So the proof that there is no residue at z goes to infinity is a bit involved. So I'm going to be somewhat heuristic. I'm happy to talk about it later, but it might be a bit long to talk about it here. But I'll try my best. So basically, MHV is Parke-Taylor, and that we showed in different ways. But beyond MHV, showing that the pole at infinity goes away is more involved. And it relies on the fact that you can define MHV like Feynman rules. So what do I mean by that? I mean that any kind of helicity sector amplitude in Yang-Mills, I can write as products of Feynman rules that all look like Parke-Taylor factors with one leg off shell. Okay, so one leg off shell Feynman rules. So let's look at what this looks like for NMHV. So, okay. I should just say over here that when I say NKMHV, so NMHV, N squared MHV, all of that is next to MHV, so next to maximally helicity violating amplitude, next to maximally, etc. Okay? And so this is an amplitude which has minus signs, k minus plus 2, yeah, times, and then plus for the rest of it. Okay? Yeah. So good. So when I say beyond MHV, I mean the helicity sectors that have more than just 2 negative helicities. Good. So I can now construct all of these. So like plus plus, and then the last one. Yeah, the last 2. Sorry, we're at NMHV. Will be a minus, right? So this has 3 external negative helicities, and I managed to construct it by gluing together some MHV-like Feynman rules, okay? And I can keep doing this. It's a somewhat fun exercise. So like if I try and do n square MHV, for example, then I just take this. So this would be plus, minus, minus. Yeah. So I can keep adding minus helicities. So this is actually, I think, n cube MHV. So I can keep doing that. I can glue together MHV like Feynman rules in order to get all the NK MHV amplitudes. Okay. This, of course, doesn't still say anything about the Z behavior or what happens at Z equals infinity, right? So to do that, we need to figure out what I mean when I say an MHV-like Feynman rule. Okay, so the MHV amplitude is the Parke-Taylor factor, so it's this over here, right? But what happens when I take one leg off shell? What do I mean by that? So here, or here as well, right? So I need to specify basically what is lambda p. So, okay, lambda p, so angle p. What do I mean by that? This is not, if p is some intermediate momentum, then angle p is not well defined because p is not on shell, right? So there is a choice you can make in what you call angle p and what you call square p, right? The only thing that needs to be true for a off-shell p is that when I do something like this, this equals I with the sum over all of the intermediate momenta like this. This has to be true. Okay, so there's some ambiguity in how I define angle p and square p, and I'm going to define it in this way. Okay, so for those of you who like spinor notation, this is p acting on square n. Okay, so now that I've done this, and all my internal gluons are now going to be defined in this manner, right? And I'll remind you that I don't need to tell you what square p is because all of the Parke-Taylor factors only have angles in them. This one? So this is just p a dot acting on lambda tilde n a dot. Yeah. So it's this, basically, p acting on square n. So what this means, once I make this assignment, all of my internal gluons don't have a factor of z in them, right? Because I'll remind you, square n is unshifted. Okay? So there's no factor of z now in any of the internal gluons. Okay? What about the external gluons? Well, I know exactly which external gluons I have a shift in. Right? I have it in n and I have it in 1. Now, because both n and 1 are going to be part of Parke-Taylor factors, and angle 1 is unshifted, the only shifted external gluon is going to be n, right? So all internal gluons don't have any z dependence. Okay, are, what should I say, independent of z. And then all external gluons are independent of z except the nth gluon, right? So that will contribute via this. Now, because this, again, it comes in the form of a Parke-Taylor factor, as long as the nth gluon is positive, it's going to come with -2 powers of z. Does everyone follow that? That's basically saying that if you have because your amplitude is little group covariant, when you shift n, the angle, and n is a positive helicity gluon, then the amplitude has to go as 1 over z squared. Okay? Here I've ignored propagators and things like that, but this is just the gluons for now. Okay? Now, so all this to basically say that an of z has to go to 0 as z goes to infinity. As I said, I ignored the propagators when I did this, but all propagators are 1 over p squared, which means that they can either be constant with z or they can go as 1 over z, right? So still, the argument holds that an of z has to go to 0 as z goes to infinity. Okay, so that was a bit technical, but basically this allows you to then say BCFW works for all NK MHV Yang-Mills amplitudes. Okay. Good. So actually, this thing that I've been saying about MHV and KMHV, you can use the fact that you can actually use recursive arguments to show that you can't have an all plus amplitude, right? Because if you look at what kinds of, so if for example, if I try and look at how to construct an all plus amplitude like this, yeah, it would have to, in the BCFW construction, it would have to come from a left, a right, where at least one of these has to be an all plus amplitude itself, right? If it's hard for you to see that, let me draw the actual diagram. So it's plus, plus, minus, plus, and then this has to be all plus, right? Good. So because this is the only BCFW term, AN all plus can only exist if A3 plus 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 exists. Okay? And you can show that for A3 plus 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 to exist, it will have to come from a coupling of mass dimension higher than the G Yang-Mills coupling, right? Yaroslav already showed that with the F cubed term. Okay. So a very similar argument allows you to also rule out something where this is not plus but minus. Okay. And we'll see in the next lecture actually that this fact that amplitudes like this vanish is an immediate consequence of supersymmetry. Okay. And the fact that Yang-Mills, non-supersymmetric Yang-Mills, is just a truncation of supersymmetric Yang-Mills is actually what allows you to continue that statement to the non-supersymmetric case as well. Okay. But yeah, we'll see that in the next lecture. Okay. For now, let's talk about what other situations this works in. Okay, so other examples. And I think the most important one is for BCFW, definitely the most important one is gravity. And I remind you that gravity, similar to Yang-Mills, it has this Einstein-Hilbert-Lagrangian, right? And that's just, that basically only contains R, right? With the minus square root of G. So that is what the Lagrangian or the action has, right? But of course, when we're dealing with perturbative gravity, then you expand around flat space, for instance, right? And when you do that, you get a bunch of corrections to this. You get a bunch of interaction terms to this Lagrangian. So you have something like H, you have a kinetic term, you have a cubic term. Every single term, basically. And of course, all of the couplings are related to one another, exactly as in the case of Yang-Mills. Okay? And that allows you, again, to show that the pole at infinity vanishes, and so you can use BCFW. Okay? Good. So this is an important example where BCFW actually works. Good. All right. So in the last part, let me move on to all line shifts. Okay, so here, rather than choosing two of the lines to shift, I'm going to choose all of them and introduce a parameter z in all of the lines. Okay, so what is this going to look like? I'm going to have some shifted momentum pi tilde, which has shift in this way. Okay, so this is some new vector that I've introduced, ri mu. So for each of the external legs I, I've introduced one vector Ri mu, right? But for all of the external legs, I have the same complex parameter Z. All right. So I just like to count over here that this means that there are 4n new parameters. Okay? Now, just like in the case of BCFW, I want an of z to be a well-defined object, which means that I need that pi tilde squared needs to be 0. Okay? And you can check that what this means is that, so okay, actually let's just do it. So it's pi squared plus 2r dot p z plus z squared r squared equals 0. Yeah? So what this means is that there's one condition that says, sorry, there's i's on all of this. I. This means that pi dot ri equals 0, which is what Lance was saying before, and ri square equals 0. Okay? So this is 2n conditions, right? 2n conditions on the new parameters that we introduced, Ri mu. So this is a total of 2n parameters then, after I've made sure that these constraints are satisfied. Okay? The second constraint that BCFW satisfied was momentum conservation. So I want that the sum of pi tilde mu should be equal to 0. Right? So this is another 4 conditions, which means I'm still left with 2n minus 4 parameters. Okay? So as long as 2n minus 4 is greater than or equal to 0, so n is greater than or equal to 2, which is a necessary condition for it to be an amplitude. As long as this is true, you can construct such a shift, right? That's not to say it's a useful shift or you can do anything with it, but you can construct it. Okay? Okay, good. So the next thing that we'll have to do is to figure out how an of z scales with z when I do such an all-line shift. Okay, now because I've shifted every single one of my momentum, right? So each of these has become pi tilde. When I'm trying to see how my amplitude scales with z under such a shift, what I'm basically doing is counting the mass dimension of my amplitude. Okay, because I'm shifting all of my momenta. Now, clearly, what I'm not counting correctly is what the polarization vectors are giving me, right? But for now, let's just count the mass dimension of the amplitude, right? So an, as we saw before, is 4 minus n, which is the sum of the mass dimension of the coupling and the sum of the mass dimension of the kinetic part, or kinematic part. And this is what we're interested in. I have some time. I started late.
Yeah, minus 2 minutes.
Yeah. All right. Good. So because what we want to do is construct A recursively, we have to start with some valence, some seed amplitude, right? In the case of Yang-Mills, that was 3-point amplitude. In the case of gravity as well, that's a 3-point amplitude. Here, let's be general. We can start with any seed amplitude, and let's say it has V external legs, right? So that tells you that Gn has to then be n minus 2, V minus 2, Gv, okay? Where V is, where the seed amplitude has V legs, so 1, 2, ... V, and Gv is the mass dimension of that coupling. Okay, so good. So this allows you to see that then Kn, you can figure out what the mass dimension of Kn is. One last thing that would help us in reducing this, basically, in reducing how An of z what power an of z goes as when z goes to infinity. You want to reduce this number, right? So to reduce that number, you can do the following. You can shift angles for positive helicity particles and shift squares for negative helicity particles. Okay? And what that does is basically does a little group transformation in a way that you're not counting any extra factors that come because you have to be little group covariant. So what that means finally is that if an of z goes as z to the power, then that power is 4 minus n minus n minus 2 over v minus 2 gv minus a sum over the spins. Okay. So this is rarely a negative number in theories that you'll be interested in. Okay. So what you have to do is you'll have to modify your integral in a way that introduces some powers of z at the bottom over here. Okay? And once you do that, as long as an vanishes on these points, so you're not introducing any new poles, you can construct a recursion relation. Okay? And the example I'm going to give is not going to be an example, it's going to be an exercise for time. And the exercise is as follows. The exercise is if you know that an vanishes in 3 dimensions, okay? You know that there's a special point, which is that in 3 dimensions, an vanishes, okay? In addition, you know that in 4 dimensions, an goes as z to the 0 as z goes to infinity. So I've given you these 2 facts, right? Can you construct a shift, so a shift that looks like that over here, and a recursion relation that then shows that an in 4 dimensions must also vanish? Okay? So the claim is there exists a recursion or a recursive argument that allows you to make this claim as long as you assume 1 and 2. Okay? And remember that in order to do this, you're going to have to find you're going to have to do an all-line shift, and then for some special location in z, an is going to vanish, right? And then that is what you're going to have to introduce into your integral. Okay? So this is an exercise. I was going to show it as an example, but maybe we can have questions instead. Yeah.
Okay, great. Thanks a lot. So questions, comments? Yeah, let me make one comment because I got these questions and I heard these questions as well now. There is a little bit of confusion. What does it mean, a contact term in this context? Because there is a contact term in Feynman diagrams. If you do 4-point Yang-Mills calculation that Shruti showed, there is a 4-point Feynman diagram contact term. However, and then there is a question, well, it doesn't have any factorization channel and so on. But the Feynman diagrams are not gauge invariant. Yeah? So the 4-point Yang-Mills contact term is there just to fix the gauge invariance. Yeah? It's fixing gauge invariance. At the level of amplitude, you don't have any contact term. The contact term would mean to write a kinematical expression which has no poles, and that you cannot do. Yeah? So if there is a kinematical term that you can write with no poles, you have in trouble with the recursion relations, because that is not fixed by the factorizations and you cannot recurse it. But the fact that there is a contact term at the level of Feynman diagrams means nothing, because Feynman diagrams are not gauge invariant, and we are explicitly working in gauge invariant setup. Yeah. So yeah, I got this question as well in the morning. I kind of was thinking about it, that was what people were asking about. So let me just make this comment. Okay, more questions in the back?
This BCFW or this MHV Feynman rules you mentioned, that's already in tree level, or you could also do it at loop order?
So there is a version of recursion relations at loop level, but this only works at tree level because you have to assume that those are the only poles that exist in your amplitude, and those are the only singularities in the z-plane on the topmost board over there, right? And that's only true when the only singularities come from propagators. Once you have loops, you have branch cuts and other more complicated singularities in AN of Z.
But there is a version of this, extension of this to the loop.
I wouldn't call it, well, there is some recursion arguments that you can make at loop level for integrands. I guess Lance has more to say about that, but this exact formula doesn't work beyond tree level. Yeah.
Yeah, so I don't deal with integrands anymore. So no, but you're absolutely right. You can't run a recursion relation like this because the loops have cuts in them. So they have logarithms. So you don't have a meromorphic function of z. It has branch cuts all over the place. But you can actually do something. You can determine the branch cut parts from generalized unitarity, which I think Yaro is supposed to talk about later. If you know all the cut parts, you can subtract them. And then the leftover thing you have is rational. And then you can do something very similar to this, but it's slightly more complicated because it has other residues besides the ones shown there.
Yeah, I can.
So-called spurious poles, which only cancel between the cut part and the rational part. So it's more complicated. So that's one possible way to do it.
Okay, thank you.
Okay.
May I have one more probably very trivial question? When all the helicities are the same, what's the physics there which is vanishing here?
Well, sorry, what is the...
I mean, what's the physical argument there? I mean, why they vanish?
So I don't know if you would count this as a physical argument, but so at tree level, all gluonic amplitudes in supersymmetric Yang-Mills and in non-supersymmetric Yang-Mills are the same. And in the next lecture, we'll talk about on-shell supersymmetry, and we'll talk about why, if you have supersymmetry, such amplitudes have to vanish. And then because gluon amplitudes are the same for supersymmetric and non-supersymmetric theories, these amplitudes also vanish. Yeah. Yeah.
So you mentioned two ways to shift the external momentum. So I'm wondering why the BCFW shift is not enough when we apply different kind of shifts. Like,
it's not that it's not enough. Depending on what the theory is that you're trying to recurse, you may or may not be able to exploit the special property of that theory with a BCFW shift. So for example, in this case, there is no way of introducing anything in your integrand that would cancel or would take into account the fact that there is this zero in your amplitude if you just have a BCFW shift.
So you are saying that for one particular theory, if I do BCFW shift, it doesn't have a good behavior at d goes to infinity. But if I do the all-line shift, it's goes to zero at larger z.
Right. So that might be the case. So if you're looking at a new theory and you don't know what kind of behavior it has, you can start with BCFW, see what the behavior is, try an all-line shift, try a 3-line shift. You can basically play with it to see at what point can you use the symmetry of the amplitude, use the zeros of the amplitude, basically, to subtract those zeros out inside of your recursion relation.
Okay, yeah. Thank you.
Okay, more questions? If not, let's go to the coffee break, and thanks, Shruti, again.